So you can put this one likely here. That would be the ideal height around. I'll help you with that. You want the other one too, or are you good?
Yes.
Is that one for you?
Yeah. Hello. Yeah. Thank you. Good morning, everyone. Being the last speaker of the conference, it's very difficult and to catch the attention of the audience. Anyway. Okay. So I'm Ravi Kashikar, research assistant professor at University of South Florida. So this work is on the electrocaloric effect in the BZT systems. So we are investigating the effect of polling. Before that, I thank the organizers to give me the opportunity to present our results. And this work is in done collaboration with the experimental folks from India. So it's a Indian Association of Cultivation of Science. So this is an institute where Raman carried out his famous experiment, Raman scattering. And we are the theoretical calculations and analysis has been done from USA Tampa under the supervision of Professor Inna Punamareva and Sergey and our PhD student Shola. So the funding agency, it's the Department of Energy. So this talk is going to be on the electrocaloric effect in the BZT systems, and we wanted to know the effect of polling on that. So it will be so mostly it will be revolving around these three terms. So I don't go beyond that. So yes, and as the previous speaker Veronica told about the electrocaloric effect, so it's a reversible change in the temperature and under the adiabatic application of the electric field. So it can be measured in two ways, direct and indirect method. So the direct method from the experimental side is a bit tedious. So people normally try the indirect method and using this Maxwell relation. And the theoretical perspective, we can use both the direct and the indirect method, and it gives similar results. So one of the way to increase the change in the temperature is to apply high field. So that's what it has been tried in 2006 in the PZT thin films, where they able to apply the field, the electric field up to the 776 kilo per centimeter in the PZT thin films, and they were able to get the change in the temperature around 12 Kelvin. So after that, there is an exponential increase in the interest of the materials to get the high change in the temperature in the thin films. So this chart summarizes that there are many types of materials like thin films, ceramics, where the electrocaloric effect has been discovered. So as I told, the basic idea to get the high change in the temperature is one, of course, the material, and the second one is to apply a high electric field. So here is the list of materials. You can see it starts from the PZT systems, and there are many materials in that list where people were able to get a very high change in the temperature by application of high field. And this is a very short list about that. However, we are interested in the lead-free PZT systems, lead-free system, that is a BZT system. So in these systems also, you can see people have already tried it from the experimental side. The large change in the temperature is observed up to 43.6 Kelvin. Yeah, of course, the reproducibility is a big issue in these works, and we wanted to address that part also in our work. And you can see the field here; they have went up to 1,500 kilo per centimeter. And based on these, our experimental collaborators were interested in these BZT systems, as they were working on some other part, like the role of oxygen vacancies in these calcium doped, zirconium doped BTO systems. So, and they were able to also got interest to know what will be the change in the temperature in these systems, both in the bulk and epitaxial thin films. And when they tried their work in the on the bulk systems, you can see this is the experimental P loops on the bulk of barium, calcium, zirconium, titanium oxide, and they were able to apply a field up to maximum 34 kilo per centimeter. And the maximum change in the temperature, the electrical change in the temperature that they were able to get is only the 0.75 Kelvin. So thinking that they were also able to capable of applying a high field, and they went up to 1,000 kilo per centimeter, thinking that the change in the temperature will be very large. But surprisingly, that was not an outcome. So that's what I wanted to show from their observation and how we tackled that from the theoretical perspective. So here is the result on the thin films. The films were grown on the STO substrate with the LSMO as electrodes, and the films were of thickness, if I remember, it's 120 nanometer, and this is the P loops from the experimental data. And the field, the maximum is around 1,000 kilo per centimeter. And the interesting part here is that you can see that the temperature that they were able to get the P loops is up to 500 Kelvin. And still the films were in the ferroelectric phase. The P loops are not closed. The area here in the loops are not closed. So which means that the films are still in the ferroelectric phase, which is, 500 Kelvin is a 140 Kelvin above the Curie temperature of the bulk. We know the phase diagram of zirconium versus temperature, and we know the TC of those different concentrations. And for the 10% zirconium concentration, the TC is around 360 Kelvin. And but we know that the TC changes with the thin films also. But that's not a case here. So the films were when they applied a field up to 1,000 kilo per centimeter, the loops are still kind of a ferroelectric one. And the second thing that's another discouraging part is that they got the change in the temperature up to only 1.2 Kelvin, which is kind of discouraging. If you see in the bulk, they were able to apply around 40 kilo per centimeter. And here it's up to 1,000 kilo per centimeter. So of course, one will expect that at least not the 30 times increase in the change in temperature, at least go up to 20 Kelvin or 15 Kelvin. But the maximum change in temperature here is a kind of 1.2 Kelvin. So here is the suppression is happened in the electrical effect, if I say that. So the two puzzles, what they offered us is that first, film remains in the ferroelectric phase, 140 Kelvin above the known Curie point, and the application of this high field has suppressed the caloric effect. So with this, we started doing the simulations using the effective Hamiltonian technique. So here are the computational details of that. So the closest system that we were able to model is the BZT, that's without calcium, that's a barium, zirconium, titanium oxide, and with the same concentration. And we also able to have the range of field is from a very low to very high, going from 50 kilo per centimeter to 10,000 kilo per centimeter. So, but I will show the results only the three important fields that we were able. Here I will show the only three important amplitude of the fields, and it's the AC field, and on the supercell of 30 cross 30 cross 30, and we have done the both direct and indirect method, but I will show the results of only the indirect one, which can be linked to the experimental results. And yes, this is the P loops from the simulations, from the MD simulations. So this is for the 50 kilo per centimeter. So you can see there's a clear transition from ferro to para. And this is the color barrier is the temperature range, 350 to 500. And once we increase the amplitude of the field, going from 50 to 5,000, the loops they're not closed. The films are still in the ferroelectric phase. I mean, the system, the supercell is in a still ferroelectric phase. And we calculated using the indirect approach, the change in the temperature. That's for all these amplitude of the fields. So you can see the peak of the electrocaloric loop shifts from the desired temperature range. So we know that this has been already observed, Professor Cohen, in 10 years back. But what we wanted to have show here is that we wanted to compare those pooled samples. For example, so here is the important curve from the simulations. So the red curve is the one, the supercell, where it is not poled. And the blue and the red one, here is blue and red one are the one data from the poled samples, I mean poled supercells. So when we compare the electrocaloric change in the temperature for these three different amplitudes, you can see that the largest one has the lowest the change in the temperature. And of course, the peak has been moved away, that's known fact, but the applied field here is constant. So the applied field is 50 kilojoules per centimeter. For the constant applied field, for the different poled samples, so we get the different change in the electrical change in the temperature. So what it means here is that, so now the polarization is not only the function of field and temperature, it's also the function of now the polling field, that's an E naught, amplitude of the field. And eventually, the change in the field, that's a reverse, the electrical change in the temperature also become the function of the amplitude of the field. So we think that this is a kind of a variable that might be hidden in the electrocaloric effect, or might be the caloric effects in the ferroelectric. So we should give a more emphasis why there are so much discrepancies in the literature when we investigate the electrocaloric effects in the material, because the reproducibility, as we know, is the biggest issue in that, and might be the polling field has been, I think, I don't say it's a neglected, but it has been overlooked. So so that can act as one of the variable in the electrocaloric change in the temperature. So and so this addresses the one question that the pooling suppresses the electrical change in the temperature. So that's the one point that we tackled the puzzle. The second point, that the films that remain in the ferroelectric phase, and that is somehow it is related to the kind of supercooling or superheating of the liquids, where when we apply and that can be stated as a superpoled state, where due to the purity of the samples, some of the dipoles may trap in some of the metastable state, and because of that, the films still may maintain the ferroelectric phase above certain temperature. So there are some transient states, metastable states, I can say. So that may come into the picture when you poll the samples with a high field. So that is then another the probable answer that we gave, and there is a simulation supported for that statements also. And so if that is the case, then how to increase the EC then? So then what we do is that, so decrease the polling field. So by doing that, this is again an experimental data, not from the simulations. So once we decrease the field, so what we do is that the shifting of the peak for the desired temperature range, and because of that, there is an enhancement of the change in the temperature, of course, because the field is now not very large, but reasonable amount. So, and when I compare with the largest field that we applied, so it's that makes us a sense here, because you can see the largest field has suppressed the data, but the lowest one, are not the exact too low, but the medium range of field will give us the maximum change in the temperature in that. So why? I mean, so you only are showing the two field. Now we went up to the different fields also. I show the final result, but just wanted to compare that with a different concentrations. So, and for that, we also did for the BTO systems, and we got the similar result. This is from the simulations again. And the summary slide here tells that we applied a different fields from the same samples. This is again the experimental data, I should say. So you can see the amplitudes are ranging from 400 to 1001, and for the different polling fields, we got the different change in the temperatures. So which confirms from the experimental itself that the polling field will play a major role in determining the change in the temperature. So I know there are, and another effect that we investigated is the strain, because the referee asked us to look for the strain also, because strain also shifts the P. But I should say that all the samples are same from the experimental perspective. Only we change the polling field. So strain is somehow there for throughout the polling field analysis. And I know there are many take-home messages, but keep mine on the top of that. So the one first message that is that the electrical effects in the ferroics show the very strong dependence on the polling field. So that can be accessed in hidden variable in the ferroic systems. And the second one is superposed samples may suppress the change in the temperature. I mean, it suppresses the caloric effect. And the discrepancies in the literatures of these caloric studies can be analyzed using the polling field. Thank you.
Thank you. Actually, I have two questions. The first one is very nice one. What is the guidance for reporting? So is it within your mind and you're putting down? So this is your mind for a long time?
It's a long time. It's an amplitude of the field which is applied for a long time. Then take out the sample and do the measurement of the electrocaloric effect. Yes, that's a very similar in the piezo material that what they do.
And the second question, so usually studies always in the cell, right?
No. No, only in the largest polling field. For example, if the polling field is very large, so in that case, the material remains in the ferroelectric phase even above the Curie temperature. For example, the 1000 kilo per centimeter here. And not if you decrease the polling field, that's not the case. Yes.
Okay, relax. But trying to understand what is point of view in your simulation. So you mean that in the simulation, if you don't do any coding, you have to move to the next stage maybe, and by coding you go towards more homogeneous state.
Yeah, the polling might create a monodomain states. So the largest field, like for example, in that simulation, the theoretical simulations, you can see the field is 5000 kilo per centimeter. So it's a very huge. So that creates a monodomain states kind of stuff.
Okay, so you start from more quickly, I guess.
No.
Because otherwise, if you have already more domain, then you fold, but then you remove the folding field, right? And then you measure, you compute the electrocaloric effect. So let me rephrase the question.
Yeah.
So if you do a simulation with a small volume, that is simulation with that volume, then you remove the field in both of them, so you have a single field, right?
Yes.
That's a permanent polarization.
Yes. True.
True one. But it doesn't change or doesn't?
So the remnant polarization you are asking about for the lab? Yes.
How these two situations differ?
So So that the remnant polarization that depends upon the temperature that you know. So and beyond the certain temperature range, that's the values will remain still there for the largest polling field.
Yeah, so I think we're all trying to understand what's going on here. So, I mean, when you say that it's, so one of the striking results you have is that you have the ferro, you know, that you have stage ferro, you have a ferroelectric behavior.
Yeah. Yes.
Which, you know, in itself is, you know, but what the origin, I think we're trying to understand the origin of this behavior, because, you know, the polling field isn't gonna change the transition temperature of the system. The only thing that's gonna change it is rain or the, you know, the thin film boundary conditions. And so where is that in the simulation?
Yes, to address that point, I have. Yes, so for that, the question that you are asking, that why the polling field is shifting the TC.
Well, it can't shift.
It can't.
Okay, explain. I don't think any of us understand that.
So, so what? First of all, the experimental samples are very pure. I mean, they're very pure samples, and that samples lacks a nucleation states, because they don't have any disorders or impurities kind of stuff. So what we did is that we calculated the dipole distribution of that high field and the high polling field and the low polling field one. So you can see there is an asymmetric distribution is there for the high field samples. So what we believe is that some of the dipoles in that the temperature range might have trapped in some metastable states here, and because of that, the still the film or the supercell remains in the ferroelectric phase. So that's what the explanation that we gave.
So you're, okay, I don't want to go on too long about that, but you're saying that you pull this into some kind of metastable state.
Yeah,
Which switches under a field, but it's not really because it's thermodynamic equilibrium.
Yes, it's a non-equilibrium states.
Okay.
Thank you. So let's thank all the speakers of the morning.
Thank everyone, and we want to thank speakers, and special chairs, and organizers, and especially Megan Holtz, who did the vocal on the living clip for that particular event. So I just got the moment everyone's waiting for. I don't know if they're here, but